Dear all, welcome back to the series of video lectures on the subject electrical measurements and the instrumentation. Today, let us discuss about the moving iron instruments MI. MI stands for moving iron. It is one of the most accurate instrument used for both. Let me repeat, it is used for the both AC and DC measurement. So there are two types of the moving iron instrument, attraction type and repulsion type. Let us see the first one, that is attraction type MI instrument. The construction, the moving iron fixed. Let us see, the moving iron means the iron which is moving in between the magnetic field, that is produced by N and S pole. The moving iron fixed to the spindle is kept near the hollow fixed coil. The pointer and balance weight are attached to the spindle, which is supported with joint bearings. Here the air friction damping is used. In the last type, that is moving coil instrument, we have used the eddy current braking, the damping. Here air friction damping is used to damp out the oscillations. So let us see the diagram. This is the diagram for the moving iron instrument. That moving arm, that is placed or it is supported with the joint bearings and pivoted between the upper and lower mechanical support, and that has been connected to the spindle with a balanced weight and a pointer, and pointer is raised over the calibrated scale as shown in the diagram. It has the fixed coil. That coil gets energized when the current passes through that coil, due to which there is a magnetic flux produced in between the N and S pole. And as there is a magnetic flux produced, that flux gets linked with the stable iron core. And as per the Faraday's law of electromagnetic induction, the force is exerted by this iron, so that iron starts moving. That's why it's a moving iron type instrument. And as the moving that iron gets moves, spindle also moves. And as the pointer is attached to the spindle, the pointer also moves over the calibrated scale. This is a simple that structure. Let us discuss now the principle of the operation. The current to be measured is passed through the fixed coil, as I told you earlier. As the current is flowing through the fixed coil, a magnetic field is produced. By magnetic induction, that is Faraday's law of electromagnetic induction. By magnetic induction, the moving iron gets magnetized. The north pole of a moving coil is attracted by the south pole of the fixed coil. Thus, the deflecting force is produced due to the force of attraction. Since the moving iron is attached with the spindle rotates and hence pointer moves over the calibrated scale. But the force of attraction depends on the current flowing through the coil. So let us see the next, torque developed by the moving iron. Let theta be the deflection corresponding to the current I ampere. Let the current increase by di. So corresponding deflection is theta plus d theta. As we discussed that the force of attraction means angle theta is directly proportional to the current flowing through the coil. So this is the diagram that we have seen just before. So there is a change in the inductance since the position of a moving iron changes with respect to the fixed electromagnet. Let the new inductance will be the L plus dl, as there is I plus di, theta plus d theta, a new inductance, that is a L plus dl. The current changed by di is in the dt second. Let the EMF induced in the coil be the E volt. So E is equal to d phi by dt, that we knew already. So phi is nothing but the flux linkage of the coil. That depends on the magnitude of the inductance and current flowing through the coil. So phi will be replaced by Li. So E is equal to d upon dt in bracket Li. It is equal to L into di by dt plus I into dl by dt. Multiplying by I dt in equation, will get A into I dt is equal to L into di by dt into I dt plus I into dl by dt into I dt. So E into I dt is equal to, yes, it is L into I di. Dt will get cancelled, plus I square, I into I square into dl. Here dt will get cancelled. So this equation gives the energy which is used in the two different forms. Part of the energy is stored in the inductance and remaining energy is converted into the mechanical energy which produces the deflection. Fine. So change in the energy stored is equal to final energy minus initial energy stored. So change in the energy is equal to final energy minus initial energy stored. So what is the final energy? That final energy is nothing but half of L plus dl into I plus di bracket square minus half of the Li square. Half of the Li square is the energy stored in the inductance. So we'll simplify this equation. So have a pause it, take a pen and write down this expression for the better understanding. It's a simple mathematics. So the simpler form of this equation is equal to, last step, Li di plus half of the I square dl. So mechanical work to move the pointer by d theta is equal to torque developed Td into d theta. So by law of the conservation of energy, electrical energy supplied is equal to energy, that is increase in stored energy plus mechanical work done. Input energy, what is input energy? That is energy stored plus the mechanical energy. So input energy is Li di plus I square dl is equal to energy stored is Li di plus half of the I square dl. Here that we got the equation from the 1.25, that is energy stored, plus mechanical energy required is dt Td into d theta. So let us simplify this. We'll get the expression for Td is equal to half of the I square dl upon d theta. So at steady state condition, Td is equal to Tc, that is deflecting torque is equal to controlling torque. So we'll equate this as a Td that we got half of the I square dl upon d theta is equal to controlling torque is k into theta. So let us solve for the theta. We'll get the expression theta is directly proportional to the I square. So in case of the moving coil, theta is directly proportional to I. That's why the scale was the uniform. But in case of the AC instrument, theta is directly proportional to the I square. It's not a linear expression. So when the instrument measures AC, theta is directly proportional to I square. That is IRMS. So scale of the instrument is not at all uniform. What are the advantages? MI can be used in both AC and DC. Basically, it is more popular in the AC. It is cheap. Supply is given to the fixed coil, not a moving coil. Simple construction, less friction error. Basically, what is the difference between the moving iron and moving coil is that in a moving iron, scale is not at all the uniform. See here, scale is not uniform as theta is not directly proportional to I. It is directly proportional to I square. Supply is given to the fixed coil, not a moving coil. Simple construction and less frictional error. What are the disadvantages? It suffers from the eddy current and hysteresis error. Scale is not uniform, it consumed more power, and calibration is different for AC and DC operation. So this is all about the moving iron instrument. Thank you.